Welcome everyone to this explainer. Today, we are looking at an absolutely mind-bending leap in how we engineer machines to interact with the physical world. We're moving away from rigid, calculation-heavy bots and stepping into a future that feels, well, a whole lot more natural.
So here's a question for you. How do you make a robot feel without using a single electronic circuit? It sounds like a trick question, right? Or maybe the ultimate engineering riddle. I mean, if you've got no wires, no silicon chips, no processors, how on earth does a machine process the sensation of touch? Well, researchers at the National University of Singapore have actually just solved this exact riddle, and the answer is nothing short of brilliant.
Okay, let's dive into this. First, the soft robotics bottleneck. We need to talk about the massive roadblock that's been holding back this entire field.
You see, soft robots are made of flexible materials, which is great for delicate tasks like minimally invasive surgery or deep-sea exploration. But to actually sense their environment, they currently rely on this really clunky, heavy chain of components. We're talking electronic sensors, signal processing circuits, powered actuators, and actual computers to coordinate the whole shebang. It adds weight, it adds complexity, and honestly, it introduces crucial points of failure. If one of these traditional robots gets too hot, too wet, or too pressurized, those fragile electronics are completely susceptible to disruption. So the ideal solution scientists have been chasing is something lightweight, purely mechanical, and highly durable. Something with literally zero fragile electronics to short circuit.
Which brings us right to our next section. Enter the MESOFs. This is a groundbreaking solution recently published in the journal Science Advances by Professors Benjamin T. and Cecilia Laschi.
Now, MESOFs stands for Mechanical Soft Force Sensor, and the absolutely crucial point to understand here is the complete absence of an electronic chain. There is zero computational processing happening in the core sensing loop. Zero. It's a purely mechanical structure that detects multi-axis forces, meaning forces from different directions, and converts them directly into fluidic actuation. Basically, the force happens and the fluid reacts. It is elegant simplicity at its finest.
Moving on to Section 3, Translating Touch to Action. Let's reveal the genius behind how this 3D-printed porous structure actually works.
Imagine this 3D-printed soft structure. It's got this central pillar surrounded by 5 fluid-filled chambers, 4 horizontal ones and 1 vertical. Okay, step 1. A physical force pushes on that central pillar. Step 2. The pillar naturally tilts in the direction of the push, which compresses the specific fluid chamber on that side. Step 3, that compression literally drives fluid straight through some soft tubing. And step 4, the actuator at the other end responds. That's it. A physical push becomes fluid movement, which directly becomes robotic action. No microchips required, no lag, just pure physical reaction.
Now you might be wondering, okay, if there are no electronics, how do we record data to actually train these robots? Well, to get an electrical readout without compromising that mechanical core, the team used a passive circuit. As the displaced fluid moves, it pushes tiny magnets past 3D-printed metal arcs. This changing magnetic flux induces voltage pulses. It is exactly the same principle as a bicycle dynamo, generating electricity just from the physical spin of the wheel. The number of those pulses tells you the exact magnitude of the force. So you get this perfect data readout without needing a single powered electronic sensor inside the mechanism. Now, what's really interesting about this next section, real-world robotic applications, is how they actually put this theory to the test. The versatility here is just incredible. They rapidly tested this in a bunch of diverse ways. First, a soft glove for weight prediction. They embedded miniaturized MESOFs units, literally the size of a green pea, to detect grasping forces at the fingertips. Second, a haptic feedback pad for teleoperation. Third, a droplet controller for medical diagnostics, steering liquid without any software. And fourth, they created these directional hair-like flexible structures. This just proves the incredible scalability of the design.
Actually, I really want to zoom in on that haptic feedback pad for a second, because this case study is wild. They had a completely blindfolded operator successfully controlling a robotic arm's grasp through touch alone. The force detected at the robot's gripper traveled as physical fluid pressure straight to a pad on the human's fingertips. The human literally felt the exact fluid pressure of the robot gripping an egg, a wooden block, and a water bottle. So the operator knew exactly how firmly to grip without seeing a thing. And thanks to that dynamo effect we mentioned, those signals were recorded and replayed, teaching the robot to replicate that perfect grasp all by itself.
Next up, surviving extreme environments. This is the ultimate test for any hardware, surviving conditions that would instantly fry a standard computer chip.
Just think about operating in 90 degrees Celsius.
That's 194 degrees Fahrenheit, basically scalding hot water. The EmiSofts maintained completely stable performance in those conditions. A standard electronic sensor would warp, short out, or just completely melt down. But this purely mechanical fluid system, it just kept working perfectly.
And what about extreme pressure? Well, they tested it underwater at a depth of roughly 11 meters. Because its fluidic channels are open-ended, the internal pressure actually equalizes with the surrounding water pressure. That means it functions flawlessly without getting crushed. It only ever reacts to the specific, intentional force applied to it.
So, the crucial point is, this system is 100% immune to electromagnetic interference, with literally zero electronic components inside the core mechanism. Standard electromagnetic disruptions that would completely scramble a conventional sensor simply do not affect it. No way! It's practically indestructible when it comes to standard electronic hazards.
Which brings us to our final section, the era of embodied intelligence. Let's step back and look at the big picture here, because this represents a profound philosophical leap for AI.
We are talking about embodied intelligence. Professor Lashke uses a brilliant biological analogy for this. Think about your own nervous system. It can react independently of your central brain. If you touch a hot stove, your hand pulls back before your brain even fully processes the pain, right? That reflex is embedded in your body. And that is exactly what EmiSofts gives to robots. Mechanical intelligence embedded in the physical body itself, producing sensory motor behavior with absolutely no need for a central control system.
I love this quote from Professor Benjamin T. He says, "We took a unique approach because we were inspired by nature's ability to scale tactile sensors in many different environments, simply using cells, which are essentially largely fluid. By mimicking the fluid nature of biological cells, they've unlocked this extreme robustness. Nature already figured out that fluid is the best way to scale touch in harsh environments, and we're finally catching on and applying that to physical AI." To really put this into perspective, let's look at robot-assisted elderly care, which is a vision shared by Dr. Yang-Ke Liu. Standard robot assistance relies on computational lag. If someone starts to fall, the robot's camera has to see it, send data to a processor, calculate the sudden load, and then command the motor to catch them. That takes precious milliseconds. But EmiSofts assistance, it's an immediate, instinctual reflex response. The robotic arm mechanically senses that sudden increase in load and reflexively provides stronger support. The physical push directly creates the fluid flow to catch the person. Instantly, no lag, just a safe physical reflex. So, what does this all mean for us? It leaves us with this final, incredible thought to ponder. If robots no longer need brains to feel, what instinctive reflexes will they learn next? We are entering an era where machines possess a true sense of physical intuition. The possibilities for medical training, elderly care, and space exploration are absolutely limitless. Thank you so much for joining me for this explainer today. Keep questioning the world around you, and I'll catch you next time.